Okay, welcome colleagues to our final day in our grades 1 to 3 science skills workshop series. We'll begin by asking Miss Christine Rudd to open for us in prayer.
Okay, let's bow our heads. Most righteous and eternal God, we want to thank you today, Lord, for bringing us to this afternoon, Lord, where we can come together and discuss our children, the business of our children. I want to thank you today for each and every person that is here. We want to pray also for those who are coming on, but whatever the situations are, they're not here as it. Lord, we pray for our moderator this afternoon. We pray for every participant that when we leave this meeting, Lord, we would have learned so much, oh God, to advance our children in the knowledge of science. But I pray you cover each and every one of us under your blood. Have your way and let your will be done. In Jesus' name we pray. Amen.
Amen.
Amen. Thank you, Ms. Rudd. All right.
You're welcome.
So, welcome again, colleagues, to our final day in this, our grades 1 to 3 science skills workshop series. I hope you are here to learn a whole lot, to be excited and immersed in all the things that we can do to improve and develop science skills at the grades 1 to 3 level. All right. With us today, we have our presenters who will be taking us through this session. All right. So we have Dr. Marvadine Singh-Wilmot from the University of the West Indies, Department of Chemistry. She's a lecturer and assistant dean, and she will be sharing some ideas and some work that she has done with children at this age level, at the primary level, and how she would have helped them in their discovery, right? Where science is concerned, all right? Before we get into that though, let me introduce Dr. Lennox Rowe, Senior Education Officer in the Science section in the Curriculum Unit, all right? And joining us later, I think, should be Ms. Carol Baker, Education Officer for Biology, also in the Science section of the Curriculum Unit. All right, so we'll get straight into our afternoon's activities. It promises to be intense. I would advise that you participate as much as possible and do not leave your screen for 1 second because you may miss something. All right, over to you, Dr. Singh-Wilmot.
Thanks, Dr. Taylor Campbell. Let me say good afternoon to all our teachers and all colleagues who are online. And just thank you very much for allowing me to be a part of this. I am going to share for a few moments. I'm going to begin by sharing my slides with you. And we are going to talk a little bit about this business of science skills and practices. You know, there's something I say to people all the time, to young people I have to deal with. If I could give a child one thing, I would give him passion. Passion for learning, passion for science, passion for a better life. Indeed, guys, passion drives people to success. And at this level, when we are working with young children, it's so easy to impart passion to them because they themselves are filled with excitement, you know, they are buzzing with excitement. And I find we have this wonderful opportunity to give them passion. So I thank you for allowing me to meet with you guys. You are the experts in this. Let me tell you a little bit about what I am the expert in. I'm an expert in rare earth chemistry. Rare earths are these metals, just like iron and copper are metals. The rare earths or lanthanides are metals. Some of them gadolinium, samarium. I won't call the other names, but you do know that you might have heard that some of them are present in red mud waste.
Hey,
that in Jamaica here, in our red mud lakes, we have significant portions of rare earths. And so and they're all around us in current and future technologies. If you take your iPhone or one of your cell phones from your color screen, to the polishing on the glass, to the circuitry, to the speakers, almost everything you know that has a speaker has a neodymium or lanthanide magnet or rare earth magnet inside of it. So these metals that I work with are present in all of these things. They're around us. The red pixels that are in our computer and television screens that's allowing us to see red, that's because of a rare earth called europium. And what I actually do with them is that I put these metals, which I call the inorganic building unit, with carbon containing groups called the organic building unit, into these frame-like structures. So I'm assembling these things at the atomic level, right? I'm putting these atoms together and I'm making them into these kinds of structures. And you can see when you look on that cage-like structure, there are actually cavities inside here. And inside those cavities, what I do is that I trap and store small molecules like carbon dioxide and hydrogen. So I'm looking to see if I can get these materials to act as carbon dioxide sequestration agents, to pull carbon dioxide from the atmosphere. We all know we have that problem with carbon dioxide being a greenhouse gas. And of course, hydrogen, as we look to use hydrogen as an alternative fuel, as we look for alternatives to gasoline and fossil fuels. Okay. Oh, wow. Dr. Taylor Campbell. My screen is not moving now. No, there we go. In this picture, my depiction of this yellow ball is just to show you that when I put these atoms together, I do get lots of space that I can do a lot of chemistry inside. Okay, so I've made a lot of these in my lab, and I call them UII MOFs. So you can see UII MOF all the way up. These are just some of them. And what you are looking on is I use X-rays to see the atoms. So these are actual pictures, and this is the way I depict them in different forms to bring out the structural features. But this is actually how the atoms are connected in 3 dimensions. So like this UII MOF, you can see that I have a square framework type structure there. Whereas, you look at these cavities in this one, and those red dots, those are actually water molecules that have been trapped inside the framework of this one. Now, here I'm doing this work right here at UWI. This is an aerial view coming up from the front gate, and the chemistry department is somewhere on that road on the Queensway. And I do this work with young people like these. Jermaine Smith is writing up his PhD now on some of this work, and Zayar Min is now Dr. Zayar Min, having got his PhD working with me. And young people like these, Kristen and Rush and Chris. And Chris wanted to go off and do his PhD somewhere else, so I got my collaborator at George Washington University to take him, and he's now doing fantastic work there. And the point I want to make here is that these young people make what I do possible. And you are the ones who empower these young people. These are our students coming up from pre-primary and primary through high school into UWI. And then I get to benefit from all the hard work that you have put in, because you're the ones who set the basis. I have gone, for instance, with Zayar. Here is Zayar. And that's me right there. And this is us at Brookhaven National Lab. Brookhaven National Lab is one of the places where one of the synchrotron light sources in the world. Anybody here watches The Flash? Anybody into those superhero type things?
Yes,
Miss.
All right, so we are familiar with this kind of thing, right? Where high energy beams of radiation, and we accelerate it, the high energy beam of electromagnetic radiation around this ring. We have strong magnetic fields, and that's interacting with the beams, and we're accelerating it. And at different points along here, we are doing different experiments. For instance, this is inside now. where the beam is coming along this line, and we can be running samples, all sorts of samples. I went there with my MOFs, my rare earth MOFs, to study them. And we can be doing a lot of experiments, seeing processes that we wouldn't normally see on an ordinary spectrophotometer, which is using electromagnetic radiation to interact with matter. And indeed, guys, I don't know about these things giving you superpowers like in the Flash, but what I do know is that it gives you super fantastic data. And here we are, you know, doing fantastic work. And these guys at Brookhaven appreciated, you know who? My student, and the brilliance of my students. Again, just making that point to you, but also making the point that the science that we are doing is cutting edge. We're doing it right here in Jamaica. And that we, as teachers of science, need to be aware of some of these fantastic things that are going on in science so that we can bring it to our students to excite them about the science. We are one team, guys. We are one team. And this team, from there to all the way up to here, we are all working together to prepare our students for the study of STEM, for jobs in STEM, and to live and work in this technology-driven environment or world. And it is true what I said, that there is prime opportunity at the preschool and primary years. At preschool is when they are most curious and receptive to learn. In the primary years, the curiosity is still there, and the reception to learning is still there. But they begin now to form this opinion of math and science. And because of that, we have a real opportunity. See, by the time they get up here to tertiary, you know, I am benefiting, like I said, from these opinions that you would have formed. And so, you know, I gotta take the time out to say thank you, but I also realize that I also have to take the time out to meet with you guys. I wish you could open your cameras and let me see some of you so we could, you know, get to know each other. It is very important that we understand the oneness of this team. All right, guys? So our mission is the same. Our mission is to provide quality care and education in an innovative, inclusive, and enabling environment. And our mission, ultimately, we do all of that so that we can create conscious and productive Jamaicans. Good? And I always say, and I hope you agree with me, I know you agree with me because I know you do this all the time, that the other dimensions of the human being, the other dimensions of our students support the academic goals. It's all good and well for us to teach them math and science, but we have to also care about their mental well-being, their social and cultural, physical and health, spiritual and ethical, what's happening in the family and home, their financial and career goals. We have to, even from the tender age, be aware of the total you and those things that support their academic goals. And we have to, whenever we deal with people in general and our students in particular, they have to trust us. We have to show them care, and we have to stimulate, we have to motivate, and we have to inspire. And one of the best ways to do that is through engagement, and science and the teaching of science gives us that opportunity to engage, because it's an exciting time, guys. If you look around the world, you know, for me, I'm excited about what's happening in the world. A little bit sad, yes, that the world has so many problems, and that's not because, well, that is because you know, that human element that causes us to know what to do, you know, but we don't do it. For instance, we know how we should treat the environment. The science has told us, yes, but we don't do it. So we now have climate change. And it is the science again that will have to fix these problems. We know how to deal with viruses and what to do when it comes to animal-human interaction, all these things, but we don't do it. And now we have COVID-19. And I'm saying, though, that it is the science that is going to help us with these most pressing challenges of the 21st century. So I think as scientists and teachers of science, and teachers at the primary level are You're teaching integrated studies. And a crucial part of that is the scientific method. So you are teachers of science. And so teachers, all of us have a great opportunity right now. And we must use and show, we must use the science to do what it was made to do. Science creates, science solves problems, but most of all, and if you walk away from my talk here this afternoon and don't get anything else from it, get this. Science is fun, and it is our job. If we don't do anything else for our students, let's do this, people. Let's show Jamaican children that science is fun, that science creates, and science solves problems, and that science wasn't made for a certain set of people, that everybody can do it, okay? I mean, we did recognize some time ago that our teaching learning process was too teacher-centered, right? And we decided that we have to create a space for student creativity and critical thinking and for building of confidence. And that's why we have this new curriculum, the National Standards Curriculum. We must be aware, though, as teachers, that our students are different these days. Their self-esteem is more important than their achievement, and they really don't like to read or write in this age of Googling and texting. And they want variety. They are so sensitized already with multimedia. Everybody has their little phone. Everybody's on Facebook, even from tender ages. They log in and sign up with all sorts of ages and get on and have their IG accounts and all these things. But you know what, guys? They therefore need engaging activities like, experimentation and live streaming. They also want to be more relaxed, and they want to be in a less formal learning environment. They don't like that formality in their learning environments, and they want their lessons to be relevant to life. And there's nothing that gives you that opportunity like the teaching of science. If you think about it, the STEM subjects are a great opportunity to engage today's learner because science is practical and it should be taught with an inquiry-based approach. So they're going to be in a setting where they're doing experiments. It's less relaxed, it's less formal, more relaxed. Yes, they want lessons that are relevant to life. Well, there is nothing else that is as relevant to life as it is the science. You're talking about COVID-19 now, and we're talking about developing new drugs and new sanitizing agents and all. Relevant to life is what we are talking about. From the kitchen to the bathroom to the bedroom, we can show them the science in action. From the cartoons they are watching and the movies like Flash, we can use the science to show them what is real, what is not real, and what is possible. And the National Standards Curriculum, I say, built on these 4 C's: critical thinking, creativity, collaboration, and communication. If we can achieve this, and indeed the teaching and learning with the scientific method as our main tool allows us to do this, allows us to build critical thinking, creativity, collaboration, and communication. And so, to accomplish our mission, I say, guys, and you tell me if you don't agree with me, we need to create amazing experiences for our children at this age. Through experimentation, we can do that. Through exploration and discovery, we can do that. We need to stimulate excitement and interest. If we can just make them understand that science and math is not difficult, that science and math is fun, that science and math is applicable to life. Come on, guys. If we can make that happen for them, introduce inquiry-based science education as that effective teaching learning technique and see if it doesn't do it. Teach the scientific method or sciencing. Teach them in Jamaican terms what sciencing really means. Is not black magic. It is real. Show that science creates and science solves problems and science is fun. But in order for us to do that, our children have to see it in us. These guys are very good at reading us. And so if we are talking something that we don't believe ourselves, they're going to know. And because they're so sensitized and so exposed themselves, like I said, we have to come good, like you would say in Jamaican language, for us to excite and stimulate them, because they are already so stimulated with their connections to what's going on through the internet. So we and the thing is, we have to guide them on how to use that information. We have a wonderful opportunity to integrate science in math, music, in everything that they are engaged in. And I'm with you on that mission. I started this many, many years ago. I recognized this, and I did a lot of work back then, and still continue to do it, just on a different level with young children. And I went to pre-primary and primary all the way up to the first form. So I went to preschools. We were in preschools with the Lab Rats program. We had a program called Lab Rats, and we were running every Saturday. We were meeting our groups in Montego Bay and Kingston, because there was a school, Fundaciones Centers, Principal Rachel McDonald. This is a private school because she was willing to invest in this. And Rachel, every Saturday we would be meeting her children, and they will just be having fun with science. But we were taking it also into the school. So we went to Winston Pretty Basic in this one that I'm showing you. And I show you how the very simple things around us in life can be used to make excitement and to teach a lesson. So, we were at this age in preschool, you're introducing them to the environment. You're letting them understand what's around them. So you let them go out and explore, and you talk about solids, liquids, gases, divide up everything that is around them in their universe into these 3 states of matter. Right. And then they want to explore some more, and they want to feel like they're scientists. So you put on their little lab coats and they get into the science lab, and the science lab is anywhere you want it to be. This one was outside the building. And so we got water. We have these little containers, these little basins there, and then they had their cups, and they got water. And we asked, what do you call liquids? And they come up with water, and describe water. And water is colorless, they say. Here comes a question. Are all liquids colorless? Is that a property of a liquid? Well, it's not. And so we met vinegar, which is another liquid like water. Well, how do you know the difference between water and vinegar? And they get in touch with their senses to make observations, so they could smell that pungent smell from the acetic acid that is in the vinegar. And they tell you that, they describe that not in those terms, but certainly in just more flowery terms, which is it's such a pleasure to listen to them when they talk. And then you extract from what they're saying and bring it together and say, okay, well, let's do some tests now. Is there any way we can differentiate otherwise between water and vinegar? And we go for some baking soda. And we talk about the baking soda, is it a liquid like water and vinegar? No, it's a solid, and we talk about that. And then we say, all right, let's put baking soda into water, and we observe what happens there. And then we say, all right, let's try baking soda and vinegar. And this is us now, trying to bring some excitement and have them do something so you can capture their attention and make your lesson around that. And so they begin to add their baking soda to their vinegar. But we said, okay, before you do that, can you add a little food coloring? And everybody wants to add red, and everybody adds red, but some people might want to add blue. So we put out all the colors out there for them, just food coloring. And they begin to add that, and they see the hissing and the bubbling, and they ooh, ah, and you hear the biggest expression of excitement and amazement. And it just makes you feel like, what you are doing is connecting. And so you make that at the end of all of that, there will be a lot of mess. They're going to end up, after we've let them see what we wanted them to see, then, and we're talking, the thing with them, I find, I find they listen probably better than the slightly older ones, these young ones. They will listen to teacher, you know, and they're very good scientists because they're also very, very observant, and we've got to let them express. So then they tell you about, and then we move them away from the scene into thinking time. We take them away to another space where their notebooks are, and we sing along with them. Thinking time, everybody thinking time. We sing because this is all coming together with the arts and the science and just life. And we allow them to think a little bit, we make it quiet, and then we ask them to write down or draw, express, because they must be able to record their observations in one form or the other. It's a beautiful lesson with the basins here. When the water runs out of the cup, or the vinegar runs out of the cup, sorry, it comes over into the basin and it changes shape. And so we get to pull that out. So many things going on, a very dynamic scene. I do not try to control it too much, just a little bit, so that we don't have anarchy, but I allow that exploration, and it's such a beautiful thing. We have even over here a bucket with water, so we had different shapes. Well, in this one, we took out some shaving cream and we did some other things, and that could allow us to talk about some other things with matter. But in the interest of time, I'm running along to another session with my lab rats, guys. And this one was possibly, this was just artistic. Indeed, this is Barrington Lord. Barrington Lord is a famous Jamaican artist. You can Google him right away and you will see his work is excellent. And so this was science meets art in the truest way. And we don't need Barrington Lord to do this, right, guys? Because we are teaching integrated studies. And so science and art and music and all of that is all together. Indeed, when you teach science, even at my level, I don't teach integrated studies. I even distill science a little bit more into chemistry, but I connect it to all of those things too, because the mission of science is to serve society. So if you don't position it in the context of society, we are not achieving our goal. But let me go back and tell you about this session. Oh, I wish we could recreate, well, we can recreate it, but I wish I could meet these kids again, because you see this one here, this is my son, Matthew. And this Matthew is 16 years old. So this Matthew don't really exist in this form again. You know what I mean? He's a different human being at 16-year-old, but his opinion of science and math has been formed. Indeed, Matthew wants to do physics and math as a career, and he's into space travel and these things. And I'm not sure if lab rats had anything to do with it, but the boy loves math and physics, okay? But back to this science meets art. I was teaching soil, okay? I was teaching soil science. At this time, my kids were doing GSAT, okay? Not PEP yet. But we were teaching it the way PEP is being taught. We were there before we got to the PEP exam. We were teaching soil and its composition and how soil is formed and the different types of soil that went on the board. And then we brought out the different types of soil. Well, in this particular one, we had them make paint from soil, and then they were using different types of soil to make craft, okay? So I should have taken it up, you know. I've got Matthew's pottery that he made back then here still, because when they formed with the clay, and they observed if they could do this with the loamy soil and the sandy soil too, you know, don't forget, we always have to ask those productive questions, and they answer it, but they answer it by doing these things that are so much fun and that allow them to be so creative that they don't even realize that they're applying the scientific method. Of course, we keep talking this to them all the time. But they were testing the different soils and if they could do this kind of pottery with the different soils. And they concluded that the clay was the best soil to do this. And then they related that back to what I taught about the basic properties of the different soil types. The beautiful thing for them though, and if you look at how intense they are, when they did their pottery, whatever they wanted to form, they did their pottery. Barrington Lord would take it and he blast it in his kiln, and then they would come back to paint it, and they have that as a keepsake. And you don't have to do this with you don't have a kiln. But you know what else I do, guys? And I have it again here. If I should have took it up. I have Matthew's hand, which I got. I just got these things from I got clay, and I pack it into one of those. At the time we had styrofoam, you know, those big styrofoam bowls, the deep one that the big soup comes in when you buy it at the restaurant. And then I oil their hands, and I let them press it down into the clay and then pull it out. The oil will allow it to go in and come out. So the imprint of their hand is inside there. And then I mix up plaster of Paris and thing that, you know, you get from the hardware. And then I put it in there. I'm casting it. And then when it dries, I take off the styrofoam container, turn it upside down, and take off all the clay. And they have their hand casted at that age. I do have Matthews on that table there. If anyone was there, could pass it for me to show you, but you believe me, or I can bring it up while you're asking questions later on. And they paint that then, you know, in their bronze or whatever. But then, you know, the creativity comes out, the art meets the science, and science becomes more relevant. But most of all, people, the science becomes fun. It's not difficult, but fun. Okay, and here in this one, they are still working with soils. This was, I gave them a mixture now, you know, with sand, and I gave them salt. And you notice here, I have water, and I have some sieves, and you know, because I brought some things from the lab, some conical flask and funnel, but we didn't need to have a lab to do that, because we had some plastic cups or some disposable cups, whether plastic or paper. And you can take your coffee filter. If you don't have the filter paper, it's the same thing. And you have sieves, and I tell them they need to give me, I put salt in the mixture, right? This is after teaching, you know, they give them a little something, they have the knowledge that then they can use to solve the problem, right? So I give them a mixture of sand, salt, some leaves or so inside of it, and I want pure sand and I want pure salt. At the end of dissolving the salt and getting it, then they have to go and evaporate that. And if you're working with anything that's hot, my kids were doing it in the sun, so they were watching that over time as it evaporated. So there wasn't much safety issue on that. But if you're using heat, in fact, when you're doing any activity with young children, everything is unsafe, even water. And safety is key and first and foremost when you are doing any kind of science, any kind of activity, but with anybody, particularly with children. So we got to watch out for the safety, because even too much water becomes dangerous for them. All right, so that one was pretty exciting. And then in this one, these are some of the members of my team. Again, I tell you, these were my undergraduate students. They're now off doing all sorts of fantastic things, but these are they who helped me to deliver this program. So we have a problem. We have a problem. Climate change is upon us, and we have, you know, people having problems growing food. Places are flooded. Some places have too much sunlight. Some places have too much water. How can we get food in those circumstances? Well, talk about what plants need to grow, no? Talk about that. Give them that information. Teach them that, and then allow them to immerse and solve a problem with it. So my problem is, how can we do this if we don't have soil? Can we do this if we don't have soil? Indeed, we can. And so we got their nutrients. We talk about what nutrients plants need. What is the purpose of soil, in fact? Once we can understand that and understand what plants need to grow, then we can make plants grow wherever, right? We needed some oxygen there. So we were we were bubbling, we were producing some oxygen here in the filter. We got a pump and we were producing some oxygen there in the water, and we had some nutrients over there, and we had the plants are here, and we were growing them in water, just giving it what it needs. The plants need some oxygen to respire too, right? To stay alive. When they respire now, respiration is gonna produce some carbon dioxide. We're gonna get some carbon dioxide. The chlorophyll will do that job, and we can have carbon dioxide combining with our water in the presence of sunlight, and food can form. You must remember that it's not, the plants have to photosynthesize, but they also have to respire. So we do need some oxygen there too. All right, so that was our hydroponic system, bringing in scientists like Tony Cheatham to interact with the students. He is the president of the Royal Society. I was the vice president at the time, because and it's simple things on the table. You see plastic bottles with water and oranges and simple things, and look at them take on Professor Cheatham. I think they were questioning at this time the shape of water. They were talking about the water molecule. It was all about water that day. They're challenging him on something, and that's what we need. We need them to think. This is them doing their food tests, you know, with starch, and they're testing for starch. They're using iodine and they're testing for starch. But look at what is important on this table, people. Certainly safety, you see them have on their gloves and so, but they're writing or drawing, they're recording, making observations. And this is them in the electronics lab trying to use battery pack right there. They're trying to light up their LED, learning about conductors, and then using it to solve a problem, to create and solve problems. The mission of science. Exciting things, you know, take them outside, do fantastic things with them, balloons, we put some helium in there sometimes, and do things that are relevant. They all went to collect waste from their homes, and then we sorted the waste, and we made our own biogas digesters in these, with these soda bottles that they pick up from the garbage. You know, fantastic things which are relevant, and show them that science is fun and science solves problems. I know my time is going, and I'm almost done, Dr. Taylor Campbell. I have to share with my people about things like these, which are so out of the box and fantastic, bring so much excitement, make science so much fun for children. They are walking on eggs. Okay, this was Easter, and they were walking on eggs. Why? Because we are talking about force and pressure. And I want them to get in, I want them to learn these words, you know, force and pressure is force per unit area, and they need to control how they distribute their the force, you know, and so regulate that, control that, so that they don't break the eggs. We've got a bucket over there for the washing of feet, because you don't want them to get some bacteria from the raw eggs. So safety is important. And when Ebola was on, they were making their hand sanitizers from aloe vera, which they pick outside, and alcohol. We did tie and dye with annatto, uniquely Jamaican, did an entire lab rat session with coconuts, bring out the coconut broom, which some of them didn't even know that people in Jamaica use these, or maybe used to use these. You know, bring out the coconut, go from the husk to the shell, to the kernel and the liquid inside, the use of the husk and the shell. Let them squeeze, get it grated for them, and let them squeeze and extract the milk, and let them talk about phase change or states of matter. Many lessons that can be made, separations. We are building observation skills and linking science to society. When we did friction, I gotta tell you about friction. We cleared the classroom, and we have to make sure that the floor, you know, doesn't have anything that can, so we fold the tables, the plastic tables, so we know that the floor don't have anything that can go into their feet and cut them. Safety is key. So they put the plastic bags on their feet, and they try to slide, and then they put some grease and they slide. Just let it go and let it flow, and let them have some fun, and let them get the message that science is fun. Then take them away from that space and let them go into thinking time. Everybody, thinking time. And you ask those questions, let them think, make their observations. They make a mess, but mess is fun. This is ice cream that we made. We made our own ice cream using liquid nitrogen. Whenever you are doing any of these things, guys, because I know you are doing it, ask those questions, those questions that foster scientific thinking. It's not about an activity, just doing an activity and it's fun and it's done. We have to embed in all of this the scientific method and foster that way of thinking. It's the way of thinking that we got to change among our people, you know. I don't care if they're going to be a scientist or a doctor, lawyer, barrister, chief. As long as we are living, all human beings must have that appreciation and must think scientifically. What is it doing? How does it feel? Focus their attention with those questions. Then get them to measure and count, because mathematics is the language of science. How much, how many, how heavy? Let them analyze by classifying. Let them compare. How are they alike? How are they different? We have to ask those relevant questions and let them think. Let them explore and encourage predictions by asking, what if? And then let them go into problem solving mode, because the mission of science is to solve these problems and make people's lives better. How could we? You'd be surprised to hear the answers. They are fantastic. So we went from the kids, because we were doing this, into making this more sustainable. So Rachel had me, here's Rachel, train her teachers in teaching science this way. And of course, you know, they did summer camps. I write their summer camps for them, because some of the activities, like I say, you can find some all over the internet, but it's the way you package it, and some are uniquely Jamaican. But I am with you guys. The intervention must begin in the early years. You can do it online too. And when you're doing it online, well, Francine is not gonna allow me any more time, so I can't talk about online right now, but do live demonstrations or ask them to go and explore and make videos of themselves. Whatever you do, however you do it, always problematize, then reflect and connect, then allow them to communicate and share. I'm telling you, I have so much more to tell you, you see, people. I have to tell you when I'm teaching sound, you know, and I make my Chinese telephone, you call it a Chinese telephone, with the cups at the end of a string, you know, so we can see the vibrations. Yes. And then I make them compose their songs and use whatever around them as their musical instrument and come perform their songs. And that is us bringing, you know, the arts and the science together, all of it, life, all of it comes down to life. In summary, guys, I wish I had the entire afternoon to talk to you. And I wish and I hope I can meet more of you, you know, sometime face to face. Because I would do this, you know, I would do this my whole life, working with kids like these. It is fantastic. So I know what your world is like. I'm saying we can do this still in COVID era, okay? And I'm saying we need to collaborate, all of us, schools, all schools, all across the different levels, home and community. We need to engage our students, and we have many tools, but we need to use them correctly and carefully. Always remember the safety element. I am absolutely elated to have been given this opportunity to talk with you, to be a part of this on behalf of the Faculty of Science and Technology. I say, you know, to all of you, thank you for all that you're doing for the students that you are producing and sending to us. And we hope that we can do more together. Thank you so much, everybody, and all the best.
All right, colleagues. Go ahead and express your appreciation for Dr. Singh Wilmot. You can say what you have to say in the chat. If you have a comment or a question for Dr. Wilmot, please indicate. All right, so she can, I see some persons, someone was saying that they wished you were able to share the online strategies that you had. But
tell them how much time you give me, Dr. Taylor Campbell, and that I'm already over time.
Oh yes.
We gotta
colleagues.
do this again, guys. We have to do this again. I'm ready when you are,
Certainly.
okay? I have
Certainly.
a board meeting today, and I put that aside to do this because I excused myself to do this because this one is crucial.
Very important. All right, we agree that we need more time, Monique and all the others. Okay, we're really hoping that you will get infected with the what do you call it now, the energy and the passion that Dr. Singh Wilmot has, and understand that science can be done anywhere, anytime, with anything. All right, thank you very much, Doc. Okay, colleagues, we are pushing ahead. We have quite a few sections to go through this afternoon. All right, and coming to us now, we have Dr. Lennox Rowe. Before he comes on, let me just say welcome to all the colleagues who joined us earlier. Sorry, who joined us later. My bad. All right, and as you can see, the entire session is being streamed, so you can always go back to the YouTube channel and go over the whole thing. All right. Great, guys. Good. Okay, so right now, Dr. Lennox Rowe, for a minute, I forgot his name. And we welcome him to introduce us to some of the strategies that Dr. Singh Wilmot mentioned. He mentioned the scientific method and many other things. So he will give us some more time looking at those methodologies. All right, Dr. Rowe.
Good afternoon, colleagues. Are you seeing my screen, Dr. Campbell?
Yes, sir. Yes, sir.
Okay, thank you very much. Okay, colleagues, good afternoon. Let me at this time just add my appreciation to the presentation. Very informative, notwithstanding the fact that I've been here, this is my third time hearing it, but it is science. We never get too much of science for those of us who are actually into science. You know, every day is like refreshing, is something new when it comes to science. So colleagues, I welcome you to this session, and I also hope that, you know, whatever we do here will add to your capacity as a teacher. And bearing in mind that you teach from grades 1 through 3, and that is the foundation for students. And if our aim here today, before I talk about our aim here today, let's look at the objectives for today. My slides are not changing. I'm going to stop sharing and re-share again.
We are seeing it, Dr. Rowe.
Okay, good. All right, slideshow from current slide, but it is not. Oh my gosh. Just give me one more second. Let me try something else. All right, slideshow. I guess I just have to work it what I have. Okay, so our objectives for today's session is that we're going to explore develop science and engineering practices and skills through investigative activities. And you would have, I don't know why Dr. Campbell didn't make the objectives known to you from the beginning, but Dr. Singh Wilmot would have gone through, you know, science processes, some of the science processes with you. So this is a continuation, and to explore strategies to be utilized to deliver concepts into my slide are not changing.
Okay, just click it one at a time. Or do you want me to share from my screen?
Please.
In the meantime, guys, let me just show you one of those hands that I told you we made. Are you seeing it?
Yes, miss.
Yes, miss. Yes, yes.
This was his little hand.
We thought that was
Yes,
your hand.
Yeah, and this is about 10 years old, right? It's still going.
Oh,
That's it.
Yes,
Oh,
we
this
see
one
it.
is Marva. This one is Mommy. This one is, no, this one is his. This one is Matthew.
okay.
Nice.
Okay.
Thank you very much, John.
very
Okay.
nice.
Now, let us look on the background for wanting to do this workshop with you. Using integrated approach for integrated studies, because number one, we know we have different, within your integrated studies, you have different subjects, like the core subjects. And then we have some drivers, our enrichment courses, right? So at the grades 1, 2, 3 level, we have an integrated approach. We don't have discrete or distinct subjects, but we try to, we're integrating a number of subjects. So not enough emphasis is placed on developing science process skills. And so therefore, we think it was prudent for us to come and share with you some of these skills that you can incorporate in your integrated studies class so as to enhance and introduce our students from as early as grades 1 through 3, some of the science process skills and engineer design process. Students they are not introduced to it from grades 1 through 3, the early years. And of course, not being introduced at that early stage, foundational stage, we have created a little problem when students would reach the upper primary school, the grades 4, 5, and 6, where they start to do discrete subjects such as sciences and so on, and affects student performance in examinations, especially the performance tasks, where focus is on assessment of science practices and skills. Now, of course, for those of you, I know, although you're teaching grades 1,
Yes.
previously, so you know about performance tasks, and you know that students need to know the assessment and performance tasks is dealing, for the sciences, deals with science skills and practices. Performance tasks for science is done in grade 5, and as a result of that, laying a good foundation at grades 1 through 3 would do the world a favor. And not only that, we know that when students transition to upper primary and further on into a high school, one of the first things I will tell you is that science hard. Man, science hard. And you know where this is coming from? It is coming from people telling them that science hard. Not that they have experienced that science is hard. But if we try to lay the foundation and introduce them to that science is all around us, everything we do every day is science, and introduce them to these process skills and so on, then the students will start liking science, and then we will stop hearing that science is hard. So as a result of that, we come to you today just to share some ideas with you that you can integrate, that you can use in your integrated studies when dealing with the science topics. Now, when we look at an overview of the integrated curriculum from grades 1 through 3, we see that there are a number of topics that are science related. Yes, the approach is multidisciplinary. It is integrated. So we are integrated in our social studies, our science, our RE, and then of course we have the drivers such as PE, art, ICT, drama, music. All of these are drivers that drive the core concepts. So my body, 1, 2, 3, from grades 1, 2, 3, our environment. These are all topics that are science related. Things in the home are science related, and we can use our science processes and science skills to teach the excited about science. So now we're going to look at developing our science concept, exploring methodology. Let's look at science. Science is approach, have a three-pronged approach. Yes, we have the science process skills and science. Then we have the science concept. And of course, we have science attitudes. Now, the reason why a number of our students believe that science is hard, because they are only introduced to one aspect of science, and that is the science concepts. So just go there and they get concepts on top of concepts on top of concepts. It bores these students to death. And as a result of that, they tend to say, man, you know what, this is hard. But what about the skills and the practices of science? What about the attitudes of science? Science process skills of science enables an understanding of scientific concepts. You see, the science skills and the science processes, they enhance our understanding of the concepts. Instead of giving students only the concepts, you know, if we enhance it by using processes and skills, then of course the understanding of our students will be greatly enabled. Science attitude. Dr. Campbell, you could enlarge it a little bit for me, please. No?
Sir, it's quite big. Probably you can enlarge from your screen. You're not seeing?
Oh. Anyway, so we say that the science attitudes also
enable them to work as scientists.
Yes. So when we look at the scientific attitudes, colleagues, a number of our students would like to tell you this: I want to be a scientist. It entails to be a scientist. Do you know those attitudes? And we need to lay the foundation from as early as grades 1 through 3. Now, how scientists work. Now, when we look at the scientific method, we have a number of steps that will go through or carry us through the scientific method. One is make an observation. Step 1. Now, colleagues, we're going to look at something here now. One of the basic skills of a scientist is that of observing. We use our senses to view our environment, to view what is going on, to observe what is going on around us. Now, we ask, from our observation, we ask questions. That's step number 2. Why? What? How? When? We ask questions after we observe. Now, from the question that we ask, because the question that we are going to ask is of a problem. Because if there's no problem, there's no need for us to ask questions. Right? A problem, we make observation, we ask question, and then we make a hypothesis. Now, teachers, I'm going to engage you now. For grades 1 through 3, you might want to break down. Mark you, there's nothing wrong with giving them the word hypothesis, but you may want to break down this word hypothesis. Let me get your feedback. What would you tell your student that a hypothesis is? As Miss Carty?
An idea that we may have about something.
May have. No, Miss Carty, don't go yet. Where would you make this, where getting this idea from? And why would you come up with this idea?
Based on what we have observed.
Based on what you have observed, or based on the question you asked, right?
Based on the question, yes.
All right, great. Anybody else? What would you tell your grade 1 through 3
In the chat,
child?
somebody has a guess.
A guess? Great.
Okay.
Anybody else?
Somebody's had a theory.
An opinion.
An opinion? An intelligent guess? I'm listening for a P word.
Problem.
Anybody? Huh?
Problem.
Prediction. Prediction.
Yeah, man. A prediction. No, mark you. I am not saying that the hypothesis is a prediction is the only terminal. I am just saying, just to get you, on the right track here. Yes, an intelligent guess, a prediction. That's a hypothesis. And you will make your hypothesis based on the question that you ask. Now, teachers, may I ask you a question? Do you think that your grade 1 through 3 student will be able to make an intelligent guess, to make a guess based on a question asked because of a problem? Talk to me, teachers.
Yes, sir.
Yes, great. Wait, Ango one teacher, may I hear?
Yes, sir.
Yes. And
I do
that's the
think
thing.
so. Yes, I do think so.
And that's the thing.
Yes.
We cannot assume that grades 1 through 3 cannot come up with a hypothesis, cannot come up with an intelligent guess. We have to challenge them. So after the hypothesis, then we're going to conduct an investigation or an experiment. Now, why would we want to conduct an experiment?
To clear up any misconception, sir.
To clear up any misconception. Anybody else?
To find out.
Sir, to find out if what they have predicted, if it is really so, or to clarify what they predicted.
Great. So we are going to carry out an investigation or an experiment to test the hypothesis. Yes, there was a question. We come up with a guess. Yes, I think this will be it. But then we have to make sure that our hypothesis can be accepted or we have to reject it. So we carry out an investigation or an experiment. By the way, talking about experiment, let me get another feedback from you teachers. Each primary school was given a science kit. Are you aware of that? That there's a science kit at your school?
No.
No?
Yes, I.
Yes?
Yes.
Yes?
Yes, I'm aware.
Yes. Yes,
No.
but we are.
Yes, sir.
Yes,
All
we
right.
are.
Yes,
Question.
we are.
Question. But are you using those science?
We have never seen it.
Good question.
We have never seen it.
So you know it is there, but you have never seen it. So I guess it's just it's furniture then. Huh? All right, teachers. The kits that are in your school, we expect you to use them. Okay? And grades 1 through 3 needs it as much as 4 through 6. So speak to your principal and make sure that those kits are available when you are doing investigation at the 1 through 3 level. So after we conduct an experiment or investigation, on next step would be make conclusion. And your conclusion is going to be based on whether or not I'm going to accept my hypothesis or I'm going to reject my hypothesis. question again, teachers. What if your hypothesis was correct? What would you do? Yes,
Could you repeat,
teachers?
sir? What if your hypothesis was correct or incorrect?
Oh, incorrect. My apologies.
Okay.
What if your hypothesis was incorrect? In other words, you're rejecting the hypothesis. What would you do?
Go back from start and see where I read it wrong.
Amen.
I would try again.
You would have to come up with a new hypothesis, though, and then go through the loop again.
All right, teachers? And then the final step would be step number 6, and that is reporting. Now, at the grades 1 through 3 level, now the reporting can be oral report. Students, now what have you learned?
I wanted to get a quote for a motor vehicle. I want to insure.
All right, can somebody mute that person? All right, go ahead, sir.
Okay, so as I was saying, we at that stage, all we do is that we cause the students them to report. They could do it orally, but as teachers, you have your creative ways of having your student to report on the investigation that was carried out. Now, look at this question. Do sunflower seeds grow taller in bigger pots? Now, which stage or which step of the scientific process would this be? Come, teachers, my time is going. Talk to me.
That's step 2.
It's a question.
Well, yeah.
Great.
Question.
Yes, you're asking your question. Now, watch this now. In order for you to come up with this question, is that you're saying, hey, let me see here. Man, I plant in my sunflower seeds. I have my pots, but I don't know whether or not I should get bigger pots or smaller pots, right? So I'm asking myself the question, does sunflower grow taller in bigger pots? So after this, what next?
Your hypothesis.
Your hypothesis. So therefore, now the question is there. Now you're going to make, probably based on experience or based on something you have heard, you are going to make a prediction or an intelligent guess. Now I'm going to put it to you. What do you think? You are my grade 1 students, and I'm asking you, now students, do you think that this red will grow taller if the pot is bigger?
Yes, sir. I think it would.
You think it would. So your hypothesis would be that the sunflower will grow taller in bigger pots.
Yes, sir.
Yes? Everybody agrees with that?
Yes, sir.
I don't think so.
No, sir. No, sir.
All right. See me, I tell you, because I know at least one person out there who thinks about I guess something happen. It don't really matter the size of the pot, you know.
And they are getting sunlight, sir.
Yeah, man. Because we're gonna keep all conditions the same, you know. Because remember now, I don't know, we don't teach fear tests, but we have to get that in their an understanding that everything else has to be kept constant, right? Only the pot size will be changed, right? So we make our hypothesis. After the hypothesis, what then?
The experiment.
Yes, you're gonna carry out the experiment. So in a grade 2 setting, for grade 2 teachers, talk to me now. In a grade 2 setting, now you might be you don't have no flower pots and buy flower pot them too expensive. How would you substitute? Because we're talking about reality here. You know?
Get a bucket.
Plastic bottles. Plastic bottles.
The plastic bottles.
And
You could use an orange juice box.
All right, good. But guess what now? If we use the orange juice box numbers, we have to get 3 different size.
That's why I said the plastic bottles. They're easier to get the different sizes in the plastic bottles.
True.
You can use
There's a
water
2 liter.
bottles. Water
Yes.
bottles.
Yeah. Oh, they ban styrofoam because we could have used styrofoam cup, not true?
But sir, you could also use the orange juice boxes because they are different sizes as well.
We can find 3 different sizes of orange juice box.
You have that big one there, that true juice. You have the true juice box.
Oh,
You
It's
have
the
the
biggest
regular
one.
orange juice box, and you have the milk, milk, those milk containers. You could use them. 3 different
Oh,
sizes.
true.
You have the mini
True.
juice box too.
Yes.
all right. Fair enough. Fair enough. So we'll carry out the experiment, right? And remember, guys, that we would want to use basically difference between the 3 sets of experiment would be the size of the container, right? So we're not gonna use red peas in one and sunflower seed in the other, right? So after we have carried out the experiment, what skill would we use? Which scientific skill would we use as the experiment progress?
Observation.
Observation.
Thank you very
Observation.
much. Yes, yes. So after we carry the experiment, what next?
A record.
You observe, record, and then draw conclusion.
Then you draw the
The
conclusion.
conclusion.
In your conclusion, and also in your reporting, what is going to come out there?
Whether the pots affect the growth size of the plant.
Okay, so you're going to go right back to your hypothesis, right?
Yes.
See whether or not you're going to accept it or you're going to reject it, right?
Yes, sir.
Yes, sir.
Right. So you see, use the scientific process to answer a question. Do sunflower grow taller in bigger pots? Everybody with me?
Yes, sir.
Yes,
Good.
sir.
Yes,
So
Yes,
let's
sir.
let's look at another process. It's called the engineering design process. Now, I'm quite sure that there's probably a teacher or two on here who wanted to be an engineer. So we are going to see now how the engineer design process is just basically the same as the scientific process, but as a little bit slightly different. So number 1, ask. Now, the number 1 here, ask in the engineering design process would equate to which step in the scientific process?
Step 2.
Which is asking a question, not you.
Yes,
Right?
sir.
Yes. So we're going to ask, what are the problems? Right? Because remember, these processes are there to quote unquote solve a problem. Number 2, after we ask what the problem, then we are going to brainstorm. Think about how is it that I'm going to solve this problem? And we could come up with 3, 4, 5 ideas. From those ideas, I'm going to choose the best one. After that, I'm going to plan. All right? So I'm going to plan how I'm going to carry out this investigation. And 4, I'm going to follow the plan and carry out the investigation. And 5, I'm going to improve. Now that I've carried out the investigation, what can I do to improve on the investigation to make it better? Or if I did not get the solution I want, what is it that I'm going to do to ensure that I get a better solution? So the engineer EDP is kind of the same. No, that's not the same. Similar to the scientific process, except that with the engineering design, we don't really have a hypothesis per se, right? But we do. Now look at this now. Problem to be solved. So we're going to use the EDP, engineering design process, to see if we could solve this problem. Protecting eggs in an egg drop. We have 2 minutes, a minute and a half for you to come up with an idea. So we'll ask a question now. How can I protect eggs in an egg drop? Ask. Now, we have a brainstorm now. So I'm asking you, how can we protect eggs in an egg drop? Anybody?
Wrap it in a bubble wrap, sir.
Bubble. So why you laugh? Eh? That makes sense, you know? Anybody else?
Put it in a padded pillow.
Put it in a padded pillow. Great. And what
Take
about
Cut
yeah,
it
take up
in
the pillow with.
styrofoam.
Huh? What are you going to pad the pillow with?
Cotton.
Cotton? Yes. Wait. So why you laugh? Anybody else? Sponge. Somebody saying sponge. Anybody else?
Styrofoam.
Styrofoam. Wrap it in newspaper.
Use paper towel.
Paper towel.
Yeah.
You think paper towel and stop an egg from crack if it drop?
I'm just saying. It's
Whoa.
an experiment.
Miss Montague, we can see you love your belly. Why?
It's up in a pillow. If you boil the egg,
Yes.
it won't break.
But guess what happened? Suppose me want me eggs with fried. Eh? But I
Buy
take
a second one.
I take your point. I take your point. Okay, guys. So now look. I have a very ingenious co-worker. Look at what she did. Parachute on the egg. Who think of that?
These are ideas from the internet, sir. It's not me do it.
That if you say you come up with that one, honestly. So these are ideas, guys, that we could actually use to solve a problem of protecting egg in an egg drop using the EDP. I'm going to ask you, teachers, I'm going to ask you, do you think that these are activities or these processes can be used in your integrated studies when you're doing topics that are science related in your grades 1 through 3 classroom?
Yes, sir.
Yes, they are.
But of course.
Yes,
Yeah, man.
sir.
Because remember, science is fun and we have to make it fun. And science is something that we do. So we expect our students to do. Okay?
I'm sorry, let me say, just note that the engineering design process can be used in any subject. So it doesn't have to be science related, right?
Okay,
You can come up with a problem in any other subject and use the
Thank you
EDP.
very much, Doc. Thank you very much. It's like, okay. Now, STEM integration. Now, Dr. Wilmot did mention, I did a little bit, and so my time is almost up, but I don't really want to dwell on STEM integration. Only to say that, you know, we do integrated studies. So therefore, this is a part of the integrative process when it comes to integrating the science, technology, engineering, and mathematics. Doc? Still STEM, Doc. Switch for me, please. My time going. Now, look at a real world scenario. Teachers, when you talk to me now, how could food be grown in this environment? And I hope you don't come up with some of the answers I heard. So go ahead.
Plant them in pots.
Greenhouse. Whatever.
Greenhouse.
Eh? Come on, guys.
Plant them in a greenhouse.
So wait, where are you going to plant? We're going to put the greenhouse.
You could put them on the top of the roof, put them in a container and put them on the top of the roof.
Put them on top of the top see there. Any top surface.
Make one that floats.
Rooftop planting.
Make one that floats.
Really? You know,
So
I hear a person's coming with this
on the
rooftop.
rooftop.
and they can be planted. It can be planted in the water. You can plant, some foods can be planted in water, like the hydroponic process. So it's water. So we can certain like lettuce and so forth can be planted in the water.
Okay, great.
Plant it in pots.
Okay, thank you very much. Set it in pots. All right, Doc, give me the next slide. Show him something now. So you see, we could have, somebody didn't mention.
I was gonna say bamboo.
Yes, floating.
Basically, it would be like on top of one of those. The floating.
We don't have no pond in your grades 1 through 3 classroom. Tell me, how would you do this activity in your classroom?
Colleagues, I'm going to ask you to raise your hand so we don't have any clashes.
Talk to me, guys. How would you carry out this activity in your grades 1 through 3 classroom?
Use one of the swimming pool, the little plastic, the rubber swimming pool that the children would use at home. Take one to school, put the water in there, and you can start it from there. Get the bamboo plants and use it.
Okay, Miss Thompson, Irene Thompson.
You could use a big pan, miss. So you don't have to be as big as a huge container, and then you can use just a huge container with water.
Okay, fair enough.
There's Stacey Ann.
You can also use one of those aquariums too for it.
Great.
Okay.
Great.
Them in plastic bottles.
Okay, there's Brunetta.
Yes, well, I'm thinking that you could use old tires with crocus bag. So you fill the tire with the dirt and you use the crocus bag to put it on the crocus bag or brown paper.
You think that would float?
Oh, it has to float. Oh.
But you know, you plant it in the water, no?
All right, there's a final comment from Gail, and then we're gonna move on. Gail David, Ellis, sorry.
Okay, I am looking at those big water tanks that you can cut, and they're big enough, wide enough to be able to do this job.
Yes, definitely, definitely. So, a question here, guys. Do you think this would excite your grades 1 through 3 students?
Yes, sir.
Yeah, man. And watch it again. They are now going to be active. You know, become an active learner. And it give you more time to, you know.
Sir, may I ask a question, please?
Go ahead.
If it's floating, right? But how would you if it's floating, it means that you're gonna have water and so on constantly. How would you deal with the mosquito situation?
Okay, but you know how to,
especially grade 1 class.
But you know how to control mosquito, right? Just put a film of oil on it.
Okay. And that would not affect the whatever plant it is that
no,
you
man.
are.
Because remember, the water would be on the surface and the roots of the plant would be below.
Okay.
Yes.
Okay.
Okay, Doc. Dr. Campbell.
That's science again, past sir. That's science again with the oil and the water.
That's science again. Good, good. You see how it is? Now, colleagues, open up or brought some ideas to you that you can use within your grades 1 through 3 classroom, where, you know, as you can integrate, use the science process skills, use the EDP, and, you know, really excite our students. Because as I said earlier, the stigma that is attached to science subjects as they go into upper primary and further on to high school. As a science teacher, I get it every day. science hard, sir. Sir, I don't want to do physics. It's too hard, right? But if we can lay the foundation from as early as grades 1, 2, 3, get them excited, we might be able to turn this thing around. So colleagues, I thank you for listening. At this time, we're going to turn it over to Dr. Campbell, who will take it from here.
You're most
colleagues.
welcome. Thank you too.
All right, can we indicate, is there a question, any question? I see, if you had your opportunity already, you can go ahead and lower your hands, so I'm not confused. If there's somebody else who has a question or a comment, you can express your appreciation for Dr. Rowe in the chat and any other comments you want to make. All right, colleagues, we're gonna move on to the next section, which will be done by myself. We're looking at developing the process skills, all right? And so let's get into it because time is going. All right, so the inquiry-based method was just on the screen earlier. In our final session, Ms. Carol Baker will be showing you the link with the inquiry-based method and activities that can be done using the integrated studies curriculum. So we'll save that one for later since we are pressed for time, all right? So we're looking at developing science skills and practices. And so to get us started, I just want you to look at this picture. I was supposed to make it bigger, but can you think of some of the skills that this scientist may be using?
Observation.
Okay, so you think there would have been kind of some observations. There are 2 raised hands. Let me find out. Mr. Hunter?
Measuring.
Yes, definitely measuring. Anything else, colleagues?
Experimenting.
Okay, all right, I guess everything can go under that. Experimenting. All right, so I'm gonna introduce you to some of the basic science process skills that should be developed from grade 1. So all of the skills on my, that's on my left, probably on your, yes. Those skills can be developed from grade 1. Ms. Thompson Davis, do you have your hand up or it's from an earlier time?
I'm sorry, I forgot to lower my hand. Let me do so now.
All right, yes, lower please. Right, so these skills can be developed from grades 1 right up, all right? And in addition to those skills, we also have some other skills. Certainly, they can develop in interpreting data. Let me this person. They can also, you know, go through creating models and experimenting. The top 3 maybe for older children. I mean, certainly at grades 5 and 6, they should be introduced to the idea of formulating hypotheses, and going up into lower secondary, they will then be able to get into identifying and controlling variables and that sort of thing. All right, so these are the targeted science skills based on the NSC. Now, also we have what we call science practices, but before we get into that, let me just test your knowledge of what these skills are. All right, so I just put a definition of a particular skill, and in the chat, you can indicate in the chat which skill is being referred to. So when we use senses to obtain information, Mr. Hunter?
Observing.
Observing. All right, we're going to ask you to say it in the chat because we're trying to move quickly in this part, please. All right, thank you, sir. All right, so that's observing. All right, what about this one? Colleagues, put your answers in the chat so we can know. Dr. Rowe, please indicate what is happening there. When we group things according to certain common characteristics.
We say classifying.
Beautiful. When we use special tools to get information, what do you think that skill is?
Measuring, I'm saying.
Measuring, that's correct. All right. And we would have stressed this throughout the entire day session, passing and receiving information. What is that?
Communicating.
Communicated. I think I hear a young one. Okay, when that person leaves this session, they will be quite adept.
A teacher.
Is a teacher? Well, sounds quite young. All right. Guess what will happen next based on your prior experience? What skill is that?
Somebody saying predict, predicting?
Predicting, yes, that's what we're looking for. All right. Use what was observed, to look at this one, to explain what happened.
Infer, hypothesis?
No, not hypothesis. So look at it again. We're using what we observed to explain what actually happened.
Drawing conclusion, analyze.
Drawing conclusions, that's it. And when we try to put meaning to the observations, that is more an inference. So that is inferring. So there is a slight maybe overlap.
Analyze.
Okay, that's inferring. All right, great. Now, we also mentioned the fact that we have science practices, all right? And so when Dr. Wilmot was showing her, the activities that they carried out with their lab rats program, over time, there were certain behaviors that the students were expected to display. Those scientific behaviors that help them to get information, to explore their environment and to solve the problems, real world and otherwise. Those scientific behaviors are called practices. So when you, for instance, plant your sunflower seeds and you observe for a particular time, there's a particular behavior that's associated with it. When you look at the growth, right, and analyze and interpret that data, that's a particular scientific practice. So there are 8 science practices. They are outlined in the NSC science curriculum. So the grades 4 to 6 curriculum have these spelled out, but they may not be found probably in the integrated studies. However, there are still practices that we think can be developed from grade 1. So we spent a lot of time talking about asking questions. Students must be given the opportunity, right? And they must be given this as a tool to question, right? What is happening around them. When they see something, they must be able to come up with a question, right? That they can investigate, or if it's a problem, to define that problem, right? To be solved, okay? They must be able to develop and use models, and we'll explain what these are in a bit. Time and carrying out investigations is a behavior in itself. Analyzing and interpreting data, using mathematics and computational thinking, constructing explanations and designing solutions. So we would have stressed, for instance, in a lot of these investigations, at the end of it, you must be able to explain what you saw, right? Good. And that is a part of the science practices. Engage in argument from evidence. If you say definitely that sunflowers will grow bigger, taller in bigger pots, where's the evidence? You must have some evidence to support that particular reasoning, right? And of course, obtaining, evaluating, and communicating information. So just to give us a better understanding of these practices, we have defined them. And what I want you to do now is to look at these definitions and try to think of what are some of the process skills that would be related to these practices. So the practices are not separate in themselves, right? So when we think of asking questions, defining problems, what sort of process skill do you think is associated with this practice? You can indicate, colleagues. Dr. Rowe, any responses? Think of a particular process skill that would be related to asking questions. Remember, in asking questions based on the definition, you're asking and refining the question that you want to investigate, right? that you want to solve. Okay? Yes? Any responses?
No, ma'am, not yet.
Not yet? All right, let's give you another second or two. Okay, so I'll start off for you. Before you can ask your question, as we saw with the scientific method, you must have seen something. So certainly observing is a skill that would be associated with you, coming up with this particular behavior, right? Good. And in asking your question, you would more than likely be predicting, hypothesizing in some respects, all right? Okay, planning and carrying out investigations, that one is easier. It is really designing your investigations and carrying them out in a particular way. So you must have an aim in mind. You must follow a particular method, right? When you get your results, you collect your results, you record, you draw your conclusions, that sort of thing. What are some skills that are associated with that practice of planning and carrying out investigations? Come on, colleagues, I know you can do it. Think about it. If you were doing the sunflower investigation, what are some of the skills? Classifying, anything else?
Classifying, yes. Observing, classifying.
Come on, there are more. Nothing else? Or certainly you would be measuring, yes. You would be recording, drawing conclusions, the whole gamut, right? Because you're carrying out an investigation. Okay, moving on. Developing and using models involves the use and construction of tools, and please note, it's not just the physical model we're talking about. So when we think of models for science and engineering, it's not just a physical model, right? When you represent ideas by using diagrams or drawings, right? Or even graphs, if you should track the growth of a plant and use a graph to represent the information, the graph serves as a model, and you can use that model to make predictions, right? And of course, provide explanations. Analyzing and interpreting data is more or less self-explanatory. You're looking at the information that you have received, you're breaking it down, right? So that you can understand what is happening, understand its meaning, all right? And so from these other practices, there are many other associated skills, right? Certainly analyzing and interpreting, right? In some cases, you may have to do some comparing, right? Some classifying and that sort of thing, all right? The next two, using mathematics and computational thinking, that represents using maths to represent relationships. So if, for instance, you were measuring the temperature on the outside and there was a gradual change or there was a change that you could see that every 2 days there was an increase by 2 degrees Celsius or something like that, right? You can basically represent that using mathematics, right? Great. Also, engage in argument from evidence. I mentioned it briefly before, use of reasoning to make your case. So if you're putting forward a particular statement, you need to support it with data. Your data is your evidence. So you cannot say October is a rainy month and you have more rainfall in October than November without having data to use to support your answer. So that sort of behavior we want students to develop in. If you're saying something, how can you prove that what you're saying is true? Where's your evidence? All right. And final two, obtaining, evaluating, communicating information. So they must be able to gather information when they carry out their tests, when they go on the outside and collect things and so on. Gather information and then critique what they have gathered, make some judgment, right? And then report on that, communicate that information in different ways. That is obtaining, evaluating, and communicating information. And the final one, constructing explanations, is, as the name suggests, you're providing explanations for what you have observed, right? And that is something that we want to develop at this level. All right, so we're pushing ahead. Now I'm going to be introducing you to some strategies. Let me just say, I didn't get a chance to say it yet. I will be posting the evaluation form link in the chat as soon as I'm finished with my presentation. We want you to complete that form. Click on that link, complete it using your regular Gmail account, not MOE School's email address, right? And when you do that, you will get access to the Google Classroom that we are populating, and you will get access to all of these resources that can help you to develop the skills at that level. All right, so I'll mention this again, but just put you on notice. So don't leave too early. Wait to get all of the session and make your evaluation so that you can also be certified when you have completed your evaluation forms. All right, so we're looking at some approaches that can be used to develop skills at the lower primary level. And some of these ideas, these approaches, let me say, were taken from an organization operating out of the UK, Primary Science Training Trust. They are linked to the Royal Society of Chemistry, and they have a wealth of resources which you will get access to as well that will help to show you how to develop skills. So there's a strategy called Play, Observe, Ask, and especially for kids, you know, kindergarten and grade 1 and so on, this is something that can be used. We know that they may have a lot of time for play. This is a planned activity, it's not just something that you just come out with like that. It has to be planned. So you have a particular concept you want to bring across. You plan something, say for instance, you're looking at buildings, part of their environment in one of those grades that they have to, look at the fact that you have schools and other things in the community, and you may be looking at buildings, right? And so you may give them a set of blocks and so on, different shapes, and get them to play with it and ask them to, make a tower, right? So you watch them play with this thing, you observe what they're doing, you listen to their conversation, right? And you may hear them mentioning some things about what must go at the bottom and so on, and what must go at the top and why. And then you ask pointed questions that will lead them into the direction of, what you're trying to stress, right? So that is the strategy, play, observe, ask. Another strategy is I see, I notice, I wonder. We'll actually do an activity with that in a minute, right? So you will get more information on that. But really it's about getting them to look deeper, look at the details, and to come up now with formulating questions, asking questions, one of the science practices that we mentioned earlier. Other strategies, encouraging independent exploration, developing talk, right? Remember, that's a part of what they should be doing, developing their communication skills, getting them to express ideas, right? Good. And to come up with explanations, developing observation skills, which we will point out in a little while, right? Outdoor learning, we can't overemphasize that this is something that you can use, you must use. And a matter of fact, now that there is COVID, you can use it to say, well, we need more space outside, right? Because outside there is so much to learn, and a lot of these skills that we're talking about can be developed, and I'll show you some ideas in the next slide, all right? And another strategy, using stories, perfect for this integrated approach that we use for integrated studies. We know generally with your stories, you can get into your language arts and all the language arts skills, but we can also use those stories as the basis for doing some other activities that now will lend itself to the development of science skills. And I'll show you an example in a minute. So what I want you to do is to focus on the jar, not on the house. And we're going to use the I see, I notice, I wonder strategy. So Dr. Rowe, I need you to work with me here. I want you to quickly indicate, colleagues, what you see. If you want to speak to me, raise your hand so we can hear what you're saying clearly. What you notice, so what you notice must go a little deeper than what you see. And then what you wonder, So you can start in the chat. Miss Carty.
Miss Carty. Yes.
All right, I see slices of lemon at the top of the jar. I noticed that the green slices are separated from the yellow slices. I wonder what could have caused that.
Okay, beautiful. All right, I see some other raised hands. McDonald.
All right.
Sorry, my bad. Yes, go ahead, Thompson.
A yellow color. I am not sure what it is, but there is lemon at the bottom. I wonder what is in that haunted house over there.
No, man, we're not focused on the house yet. We're just looking at the jar.
I'm going to read my mind. Okay, let me speak now. Sorry about that.
Yes.
I see green lemon at the bottom. I'm wondering what the yellow stuff is because I can't say it's lemon. Okay. And I'm also wondering what is in that haunted house over there, causing the birds to be on the top.
All right. I was saying we don't want you to look at the house. We just want you to zero in on the jar. All right. We leave the house for another time because we're pressed for time. McDonald, go ahead.
I see water in a jar. I notice there is a pipe on the jar.
Okay.
And I wonder if this is something to drink.
All right. That's good. I didn't hear that one before. All right. Shana, Sharif.
Okay. Okay.
Slices of lemon, ripe lemon at the top of the jar and green lemon at the bottom.
Yes.
I wonder if after the lemon gets ripe, it goes to the top and the green ones stay at the bottom.
Okay.
What's
all right? All right. So for full disclosure, with the place where I got this picture said that the yellow slices at the top were lemons and the ones at the bottom were limes. I don't know if that will affect your ideas, but all right. Remember, colleagues, lower your hands if you have asked a question or shared so that we can know who else needs to speak. Mrs. Newman, I think. Mrs. Newman, I'm trying to unmute and I can't get her. Newman? No? Dr. O?
Yes, Doc?
I was trying to get Mrs. Newman to unmute. I'm not getting her. All right.
Take Colette Logan.
Colette, go ahead.
Okay, so I see I also see them as lime as well. At the bottom, I also notice it's on the jar is on a stand thing, seems to be on a shelf. And I also notice the pipe thingy that is coming there, coming from it. I am wondering how is the pipe going to be turned on, because the thing that is supposed to turn it on, I'm wondering if that little thing out of it, you have to move it side to side to turn it on. And I also wonder if it's lemonade in the jar.
All right. All right. There's Sterling, last comment.
I see a jar with water. I notice there's a pipe on the jar. I wonder if the water can be drank.
Okay, all right. All right, so colleagues. All right, so the idea of this activity is that at face value, you can just state what you see. When you reach to the point of I notice, you want them to go a bit further, get some more details, right? So certainly mentioning the fact that you notice that the yellow looking fruit, and in this case, they were told that it's lemons, are floating at the green lines. They are sinking. But you could also go further to look at the shape. It seems as if one is cut a particular way and the other is cut in a different way, right? You know, and so you can come up with so many different things. And then for the I wonder, you want them now to start to formulate some ideas, formulate some questions. Some of these things can also be tested. Because if, for instance, we could say, I wonder if other fruits behave like this, right? Good, similar fruits, citrus fruits, if this behavior is similar, and then you can actually test it out, right? So this is a strategy that we can employ, right? And it can be done in any subject area, okay? All right, moving on. So we mentioned before outdoor learning, all right? Just showing you some ideas. So all of these ideas are from your integrated studies curriculum, right? You are doing topics related to plants and animals, habitats. And so you can actually go out and explore these habitats, right? Collect samples of living and non-living things, collect and sort and classify, right? Materials that are around them in the community, around in their homes and so on, right? From that collection, right? They are using their senses. Remember, they're using their senses to get information. Let them notice and observe the different sounds around them, the different smells, the colors, the shapes. They can, camp out, in quotation marks, of course, and record changes in the weather, record changes in the environment, right? From the data that they collect, they can, come up with their graphs showing what is happening. If you were investigating plant growth, measuring those changes and plotting your graphs, all of that is an integrated approach, right? You can see the mathematics, you can see the social studies, you can see the science, right? And you can definitely see the skills that we want to start developing coming out. All right, another strategy is called odd one out. I'm going to actually use the second one. This one may be a little simpler. Let's look at this this picture, and that how we use this strategy is that you're looking at the pictures, you're coming up with which is the odd one out, but you have to give a reason. So whatever you're saying, you must give a reason, something that would support your answer. And this is a part of engaging in argument from evidence, okay? And constructing explanations, communicating, observing, analyzing, sometimes classifying. All right, I see who was first, Stacey Ann?
Yes, Miss.
Go ahead.
Well, Miss, I am looking at them. I can see they're all flowers, Miss. But when I look a little bit closer, I can see that 3 can be planted in a pot or in a garden, and 1 should be in a water, in a pond. So
great.
the lily,
Can somebody mute that person? Sorry, I'm sorry. I'm hearing some sounds. Right. Okay, so certainly, yes, Miss Stacey Ann. So you're looking at habitats, right?
Yes, Miss.
Beautiful. All right, let's hear from next person. Colette, quickly. No?
Actually, yes, Colette's here.
Yes.
My simple explanation is similar to that of Stacey's.
Okay,
my
so you're using the same one?
Is that 3 can be planted on land, actually, and 1 in the water.
Okay, so that's your answer.
The water and the other 3 on
All
land.
right. All right, let's hear who else. Lindsay.
Angela.
All right,
Angela
just
here
a
wanted to
second.
say.
So soon come. Lindsay, go ahead.
Yes, good day. I'm noticing that the wild rose, tulip, and water lily are all single, and the primrose has a lot.
Okay, yeah, you're talking about the petals and so on, or you mean the number of flowers?
The blue.
Right.
We're talking about the flower. The flower itself, the blue.
All right, beautiful.
All the three have one, and one of them have more. That one is the only one with the many different blooms.
All right, let's go to McDonald. Thank you. McDonald, quickly.
Yes, I'm seeing here where the rose, its leaf is long, and the others are broad. So you have slim leaf and broad leaf.
All right, okay. All right, final one, Sterling.
The water lily is in water while the other three are on land.
Okay, thank you, Miss Sterling. All right, colleagues. All right, so if you have answered already, just lower your hands. All right, so colleagues, I'm telling you, you could choose any of these pictures, right? And come up with a reason why that one is the odd one out. You could be looking at the color, you could be looking at the shape, you could be looking at the number of leaves, the petals, the habitat, right? Good, as we would have demonstrated. So using this activity is not about a right or wrong answer. It's about getting students to communicate, to make observations, to support those observations with reasons, and so on and so forth. All right, so we have, and certainly, so this can be done at any level, because if we did this at the upper primary level, we would now probably go further to look at flowers, flower structure, right? That sort of thing, okay? Okay, and we would have mentioned some of the skills that would come out. All right, another strategy is called picture for talk. And of course, this is aimed at getting students to express their ideas, to develop the skill of communicating. So I want you to look carefully at this pic. I want you to think, what do you think this is? Put your answers in the chat. Dr. Rowe, help me out here. Tell me what you think it is. Of course, if you can say why you think it is so, then that is perfect. All right, which animal do you think laid this? If that's what it is. All right, because it could be, yes. All right, any responses, sir? As Dr. Rowe left me.
You have eggs, look like lizard eggs, eggshells, rotten eggs.
Right, so I hear lizard eggs. No.
Rocks, I see rocks.
Rock, or somebody saw rocks. All right, so look, zoom in, colleague, who saw rocks. Zoom in and look at the appearance, look at the color, look at the texture or something, right? And see if you still say rocks. So certainly, I guess we are agree. Dr. Rowe, are you speaking? Because you're muted.
No, Doc, I'm right here. You all say lizard eggs are fungus, snake eggs.
Yes. All right, I see Miss Sterling has a comment. Miss Sterling.
Snake egg.
Snake eggs. Why do you think it is snake eggs?
Right.
No, let her answer. Let her answer. Why do you think it's snake eggs? All right, and so when we use this activity with our students, whatever answer they come up with, we want them to be able to defend it. Why do you think this is so, right? And certainly we would agree that these are eggs, a particular animal laid it. Now, why would we say it's not chicken eggs? What information from the picture could help us?
The shape of the eggs, miss.
The shape, only the shape? What else?
Texture.
The texture, it looks a bit, I'm gonna, yes, the size as well. I'm gonna use the thing, rubbery. I'm not sure if that's the right word, but it looks a bit, something like that. Chicken eggs are a more, what do you call it now? Somebody said brittle at some point before, right? So you want to zero in on this and then get the students to come up with answers and the reason why they think that is so. And of course, you can take this further for a class that is at the higher level. You can go further now, talk about reptiles and so on, right? And the fact that is not only birds lay eggs, obviously.
Other animals lay eggs also.
These are the eggs of a cobra, which is a type of snake, right? They lay eggs, all right? Spencer, you were saying?
I was saying other animals are there that lay eggs.
Yes, definitely. All right. Another strategy, I'm going to show you here. These are paired pictures, all right? And with paired pictures, you want them to identify what is being shown first of all. So go ahead. What is this? The first picture. So if this is what, then what is this one?
They're both toads.
They're both toads. All right. Yeah. Anybody else?
Frog. Both frogs.
Is the bull ones. So you know, I don't want to fight on the bull one. All right. So in Jamaica, we call everything that we see bullfrog, but really and truly, this is a frog and this is a toad. No, look at them now, a little bit closer, and tell me what is the same, what is similar, and what is different. So here we're looking at making comparisons, right? All right, so let me go to Patricia.
Miss, the color of the color of them.
You're saying that is different?
Yeah, the colors are different.
Why do you think they're so colored?
Because of where they live. I don't know.
Yes, so yes, man, you're on the right track. So notice the frog looks a bit green, or somebody has their mic on. All right, so the frog is you can see some green spots on him.
Green to the skin.
Because of where it lives. So this is a survival mechanism, right? Camouflaging, right? All right, what else do you notice? Let's go, let's zero in on this.
Okay, run that now, sorry.
Okay, colleagues, you have to mute. Okay, Natasha.
They're both amphibians.
Both amphibians, yes.
Yes. I'm noticing that they...
Okay, just a sec. There's somebody talking. All right, let me go back to Natasha. Yes, Natasha.
Thank you. I'm noticing that the eyes of the frog are on top of the head and more bulging than the toad.
Right. And do you have any ideas why this may be so? It is okay
perhaps
if
because
you
of,
can't think of, yes, go ahead.
Yes, survival skills, habitat, perhaps.
Yes, I think the reason that was given was that for the frog, the eyes can see, he can go above and below water, whereas the toad is at the side so that they can quickly respond to movement and that sort of thing, right? Okay, anything else that is similar? Let me try somebody else. Carty.
All right. I know as it relates to the toad and the frog that the frogs are normally smaller than the toads.
Okay, all right. All right, looking at this picture, they probably don't seem that
the size
too different.
Exactly.
Right. But what else in the picture could you see?
The skin is smoother.
Aha, beautiful. So you can see that the toad seems to have more bumps, bigger looking bumps than for the frog. And we could go on, but the idea is, again, what can we do to help to develop some of those skills that we were mentioning? All right, last strategy we want to bring to your attention. I mentioned earlier using stories. So this is a story of the Three Little Pigs, and we know we possibly use it for language arts, and we can get into our sentence structure and all of that, right? But what other activities could we use, right? Use the story as that central theme, and get students to really target some science process skills. Think about it. We're talking about the 3 little pigs. What could we do with this story? What is that?
Types of houses.
Growth and development.
Okay, you can look on housing, yes.
You could
somebody said
look at the materials used.
Materials, beautiful. So obviously, one of the main reasons why the houses, some of the houses couldn't withstand the wolf was because of the material. So it's a perfect opportunity now in your science. If you want to get them focused on developing some skills to investigate materials, right? Look at objects that we can blow and why we can blow those objects, right? Go on the outside again, outdoors, and look at how things respond to the wind and link that to disasters and hurricanes and so on, right? Colleagues, if I had if I had allowed you to respond earlier, just lower your hand so I can know who else has a new comment, all right? All right, what else? We can actually know, remember you just learned about the engineering design process, get them to construct, houses of using different materials and test these materials. That is a perfect way of using the engineering design process. Look at, somebody mute that person. Looking at waterproof material, waterproof roofing, what materials you can use. And each time you're doing these things, you get students to make their predictions, right? Come up with your ideas. All right, just a sec. Let me mute just a sec. All right. All right, somebody was saying something. Could you just indicate who was that? Could you raise your hand so you can speak again? All right, Spencer,
Angela.
yes, go ahead. Yes, go ahead.
Yeah, I was saying, even today we were doing the same 3 little pigs story, and one of my students asked, why is it that the pig, the wolf was blowing and could blow down the house? And and you know what I compare it with? The hurricane season.
Exactly.
And there I started to talk about the weather. I tell them about the different weather and what happened and so on. So there it was just
like that, right? Beautiful. So colleagues, we're saying that there are opportunities for us to develop the skills. So certainly, as Ms. Spencer mentioned, looking at shelters, that is in your grades 1 to 3 curriculum, looking at needs of animals, different homes and what we can do to construct these homes, and of course, protecting the shelters from different disasters. Those are things that can be done. All right. So as I mentioned, I'm going to put in the chat the evaluation link. There's one last presentation. This is to be done by Miss Carol Baker, who is, wonder why this is okay, this is showing. Miss Carol Baker from the science section. She is the education officer for biology, and she'll be sharing now with you some specific ideas from the grades 1 to 3 NSC integrated studies, and showing you how the methodologies that we spoke about and the skills that we mentioned can come together in some of these activities for integrated studies. Ms. Baker, over to you.
Thank you, Dr. Campbell. Good afternoon, my colleagues.
Good afternoon.
I am now going to...
Good afternoon, Ms. Baker.
Good afternoon, Dr. Rowe. All right. Just give me a moment to share my screen. Okay, now we are going to consider some opportunities for developing science skills and practices within the grades 1 to 3 integrated curriculum. Now, science is all around us. I am sure that you will agree with this statement. Sometimes in life, we are so busy that we may miss this because, we're not really looking for it. But I'd like to invite you to take a look at the grades 1 to 3 curriculum, for example. Notice that you have some topics that are obviously science related, for example, my body and care and safety of self, etc. But this is an integrated curriculum, so it addresses language arts, mathematics, social studies, R&T, visual arts, and of course, we have drama and RE. Go down to term 2, unit 2, grade 1. I've highlighted that. Things in the home. Now, this is not really a science topic as it is presented here, but when you examine it closer, there are many opportunities based on the objectives outlined, many opportunities for some science to be brought out. The same thing could be said for grade 2, term 2 as well, unit 2, satisfying our needs. And go over to grade 3, you will notice in term 2, unit 3, aspects of the Jamaican culture. Now you might wonder, how will we get some science out of aspects of the Jamaican culture? This will become very clear to you. So the point is this, every single topic that is expressed in this curriculum has the opportunity for some science in, but you only have to look. Let us take a look at some examples in more detail. Grade 1, what are some science opportunities here? Focus question, things in the home and what they are used for. Attainment target, create artwork using a variety of materials and tools. Objective, create 2D and 3D models of things in the home. Of course, one of the best places to go for science is in the kitchen. There we could find flour, food coloring, salt, and oil. And the children could use this to make Play-Doh. Now, making Play-Doh is pretty much like making flour dough to make dumplings. The salt and the oil are added for preservation and for pliability. Now, there is a lot of science in this. After making the Play-Doh, the students could use it to satisfy the objective, create 2D and 3D models of things in the home. So they could use the Play-Doh to make something. Let's look at grade 2. Focus question. Why do I need transportation and how do people and goods get from place to place? Attainment target. Demonstrate the creation of art through the use of tools, themes, and materials. Objective, create 3D models of vehicles from recycled or discarded materials. Again, we could go directly to things in the home, in the kitchen, and following through with the flour concept, you flour and salt this time. Now, what could the students do with this in order to bring out some science? Well, they could make pasta. All that is required in this instance would be to take the flour dough, roll it out very thinly, and put it to dry. And immediately, the children will notice, well, not immediately, the students will notice that the properties of the flour dough will change. It will no longer be soft and pliable, but it will become hard and brittle. There is a lot of science in that. Now, this is a social studies topic, talking about how things are transported. So the students, to bring out some science, the students could be required to use this pasta, which is made to create 3D models of vehicles that are used for transporting various types of goods. Grade 3. Focus question. What is the Jamaican culture? Attainment target. Use simple material, tools, and equipment to develop skills in cutting, assembly, and decorating. Objective. Design and make different types of kites as demonstration of our Jamaican culture. Now, right here, we could go back to the same kitchen and we could extend the flower concept further. This time we'll use flour, paper, sticks, and fabric. Now, the objective simply asks the students to make a kite that would demonstrate a part of our Jamaican culture. Now, this is a perfect opportunity to bring out some science. The students, well, I was about to say that you all know how to make kites. I'm not so certain because we're living in a different age where, I mean, I don't see much kite making anymore. But when I was a child, we used to make kites. And what would happen, we made the shaped kite that we liked from bamboo strips. And then we use beautiful papers like crepe paper, kite paper, cartridge paper, or the kids could use brown paper, newspaper, book, typing sheets and color it, whatever they choose. They could make the kite from that. But in a science learning situation, how would you bring out the science in that? Well, for one, you could choose not to give the students an adhesive, because once you have the paper constructed, you would have to now paste it onto that frame. Now, this is a problem. How are the students going to solve this problem? They need an adhesive. Can they use the flour and water that you present to create a kind of glue that would work? We will look more at this later. But these are some opportunities that the teacher could use to insert some science, and in so doing, help the students to develop some science skills and practices. Now, we have identified some areas, some topics that you could bring out the science in. But just how are you going to do that? Well, to do that, you have to use an appropriate instructional methodology or approach that lends itself to developing these types of skills. These kinds of skills that we're talking about cannot be developed through lecturing. That means that the teacher cannot stand before the class and just talk or just explain something and the students listen. It's not going to happen effectively. There's a place for lecturing, but in this technological era, and based on the 21st century skills that we want to develop from very early, it is best to use an instructional methodology or approach that will help you to achieve this goal. And on the slide that you're viewing now, you will see some of these methodologies and approaches. For example, inquiry-based learning, problem-based learning, and project-based learning. You're familiar with these already, colleagues, but are you using them to your advantage and to the students' benefit? Approaches, these were also discussed this morning, not this morning, earlier in the presentation. The engineering and design process, EDP, STEM. Some activities were mentioned that lend themselves to these approaches. So let us take the inquiry-based learning methodology, for example. Now, we're not going to go in detail about the inquiry-based learning instructional methodology, but I just want to say that if you look at this list here, it gives you an idea of what should happen if you are using the inquiry-based learning methodology. These are some characteristics of inquiry-based learning. So if you're using this methodology, you'd expect that the students are actively involved in their own learning. That is, they're constructing their own knowledge through experiences. And these two ideas are based on the constructivist approach, which tells us that students are likely to learn, well, not just students, all of us, but in the context of students, they're more likely to learn when they do something, when they experience something. And it is through this experience that they will develop new knowledge or refine the knowledge that they had prior to being exposed to the experience. And I can tell you this, once they go through this kind of process, they will never ever forget what they learn. Now, the inquiry-based learning methodology is based on questioning. The teacher will ask many questions. And in some levels of the inquiry-based learning approach, the students may also ask questions. These questions serve a very important function in that it helps students to stay on track, or it helps the teacher to guide the students in a particular direction. Because if you remember, the teacher would have planned her lesson, and she has, or he, some objectives, learning objectives that, you know, he or she would love to achieve. So it means that if the students, while they're working either individually or in groups, are going way off on a particular tangent, the teacher needs to rein them in. So by asking these well-defined questions, these questions must be prepared beforehand. Not all of them can be, but these questions must be ready in so doing in order to help the students to get back on track. Now, inquiry-based learning is about investigating solutions. That means that usually students are presented with a problem that they're expected to solve. When they have gone through their explorations, their investigating, they are required to discuss their discoveries and their experiences, share with the class. Then they reflect on the new knowledge that they have gained. We will look a bit more on what is involved in actually reflecting.
Sure.
Now, the students, the activities that students create or present to their students in the inquiry-based approach are not based on recall. Learning through inquiry takes the students beyond recall to higher order thinking levels. This is very important because students, if they are not given the opportunity to exercise their critical thinking skills, then they might not move as quickly as you expect them to move, or some may not move at all. And the idea is to move a grade 1 child or a grade 2 child, grade 3 child from that level of thinking to something higher. Now, let's look at the process. The process in inquiry-based learning, the lesson will start with an open-ended question. And this question might be presented by the teacher, the student, or both of them. Then the student engages in some sort of research about the question. What does the question really mean? You know, they will go now and do simple research. They're developing their research skills here as well. So once they find out all that they need to know, or as much as they need to know about the particular problem, they conduct their investigation. And of course, this investigation can take place and should take place using the scientific method. Now, at the end of their investigation, the students present and discuss their findings. In this way, they're learning to communicate with their classmates and their teachers. And finally, they reflect on their own learning. Reflecting on their own learning means that the students are now going to think, did I like this activity? Did I hate it? Why did I like it if I found that I liked it? How can this activity be of any benefits to me now or in the future? Or the teacher can ask these questions of the students, or the teacher may give the students a self-evaluation instrument. For this level, it would be something very simple. For example, it could be an instrument, a self-assessment instrument with smiley faces, and the students are just required to circle the one that is applicable to them. That is very suitable for grade 1, but as they move up to grade 3, you can make those instruments a little bit more sophisticated. But the fact is that students must be asked to say something about the learning experience. Now, there are basically 3 levels of inquiry: structured approach, guided approach, open approach. You will find that you might come up with when you do your own readings, you might come up with a 4th one or even a 5th, but the 4th and 5th ones are usually combinations of these basic 3 approaches. Now, in the structured approach, it is teacher directed. The teacher provides the questions and step-by-step instructions that will help the students to discover the answers. Now, I want you to pay careful attention to step-by-step instructions, because some persons, they give students the steps to follow, and the students just follow the steps like a robot. That is not inquiry-based learning, and that is not structured inquiry. Remember, I said that in inquiry-based learning, a lot of questions must be asked. So while the students are given the steps, the teacher is not going to predetermine what the answers are going to be and be a stickler for the students following every step as they are presented. All that is required here is that the teacher acts as a facilitator. The students have what they need, and the teacher guides the students in carrying out these steps in order to discover on their own the answers. So the teacher will have to ask some questions. And as I mentioned earlier, that if the teacher, while circulating the room, moving from group to group, notices that the students are way off target, then this is the opportunity to offer some feedback and ask some questions that will help the students to get back on track. The guided approach. Here again, the teacher chooses the question, poses the questions to the class, and the students this time establish the direction and the methods of inquiry. That is, the children will choose how they want to go about carrying out the investigation. Again, teacher feedback by posing additional questions. Open approach. This is the approach that targets higher order thinking. And it's usually more suitable for older students who are at that developmental level. The students poses the questions and methods of inquiry. So the teacher basically allows the student free rein to come up with a question, come up with a problem, and design an investigation to find a solution to that problem. Now, some teachers might be uncomfortable with that idea. It does not mean that you're losing control over your class, or, you know, it simply means that you are going to become an A1 facilitator, because usually even in the open approach, the students will struggle. They will have difficulties, and so you have to be there to guide them from the sidelines, and also to make sure that they're not going to do anything that will explode on them and injure them in any sort of way or cause some serious problems. So you have to be there to offer the guidance that is required. Now, when you look at the curriculum, as I mentioned sooner, you will see many opportunities for sciencing. When you decide to introduce some science, you are also going to come up with an activity. It may be an activity that you create, or maybe one that you find on the internet. But before you give that activity to your students, make certain that the activity is designed or appropriate for the grade level. It should be appropriate for a grade 1 child, or a grade 2 child, or a grade 3 child. So the level of inquiry selected by the teacher is dependent on the developmental level and the needs of the particular set of students. So the open approach, inquiry approach, and the guided inquiry approach are usually not recommended for students at the grades 1 to 3 levels, because they are in most instances not ready for that. So the structured inquiry is usually recommended. And so when you select the activities that you're going to give these students, you have to make sure that the activities are consistent with what research says are the students' capabilities. How mature are they to handle what you are asking of them? If you do not do that, you will find that the students are just not getting it, and you're teaching and reteaching and nothing is happening. It could be because they are just not ready yet. Everything in life happens in stages, and as we pass through stages, it takes time. So let us see how the grade 1, how the structured inquiry could be applied to the grade 1 classroom. Now, these are some characteristics of the grade 1 child as it pertains to science. To my right, there are also some additional characteristics of the grade 1 child as it pertains to reading and comprehension and language arts skills. In science, at this level, we expect students to be able to make comparisons, to use their senses, all their senses, to make observations, to engage in simple explorations, and to draw conclusions based on what they have explored, based on their comparisons, based on the observations that they noted. So let's see that in action. Remember, I said to you sooner, let's go back to slide 4, that one science opportunity could be to help students to make Play-Doh, and then they'll use the Play-Doh for something, creating something else, maybe a favorite toy or anything that they like. Make it fun, give them the opportunity to just have fun and be themselves. All right, so we're going to look at the Play-Doh and see if we can find any science in that. Okay, so the skills that would be targeted in this activity would be the students' observational and communication skills. There are other skills that could come out, but these are the two we're looking at because these skills are the students in grade 1 are ready to start developing or develop these skills. So the teacher would start by providing the students, of course, with the recipe for making the Play-Doh, the instructions for making the Play-Doh, and the materials for making the Play-Doh. But one thing to note in this situation, this activity, you would give just 2 food colorings because you want the students to make 2 colored Play-Dohs, maybe 1 red, 1 yellow. So but eventually you're going to want them to make 3 colors, 3 Play-Dohs of different colors, but you give them only 2 colors. Then the students are guided in following the step-by-step directions for making the Play-Doh. Of course, remember the teacher would be asking some questions that are related to the science in adding the water to the flour, kneading it, and all of that. Now, next, after the Play-Doh has been made and the students have colored the Play-Doh red and yellow, the teacher could now take it a bit further by posing a question that challenges the students to solve a problem. That is, create a 3rd batch of Play-Doh that is of a different color. Now, how will the students solve this problem? They do not have a 3rd color. And so what that forces the students to do is to discuss among themselves if they're working in groups and brainstorm and try to solve this problem. It may require that they go to the internet to do simple research, or they may have maybe books available in their classrooms that could help. And because of COVID, they're at home. They may have other resources that they can check to get some information. Now, the idea is that the students would blend the 2 colors that they have. Now, I'd like to say that this activity is not targeting the students' ability to identify primary colors, because at the grade 1 level, some students might not yet have mastered recognizing primary colors and being able to say what color would be formed when 2 primary colors are blended. Because some students might not have developed sufficiently to handle that, certainly by the end of grade 1, they should be able to, but just in case, this activity is not targeting that. This activity is targeting the students' ability to make observations, communicate, and problem solve as they go through the activity. So let us say the students were able to make a 3rd batch of Play-Doh that has a different color by using something else, some other material that the teacher did not present the students with. Would that be wrong or right? Now remember, when you use the inquiry-based approach, students are allowed to discover answers. So there's no right or wrong answer. So if the students come up with multiple colors, or if they came up with a Play-Doh that is rainbow, it is not incorrect. It is how the students perceived their activity. It is their own creativity, and so it is totally acceptable. The crux of the matter is that the students would have solved the problem. They created another batch of Play-Doh that has a different color. So this is how you would bring out the science. And all of this would require the teacher acting as facilitator to ask the right questions at the right time. Now, after the students have made this Play-Doh or done this activity, they need to share with the class. This is how the communication skills are going to be developed. So remember, they are grade 1 students, so their language skills are not as advanced as, let's say, the grade 2 or the grade 3 students. They're just learning. So they can present their findings by using pictures or drawings and the use of simple words. But starting from this very primary level, they will develop the more later, and the more opportunities you present to them for using this way of presenting their work to the class, the better they will get at it. Also, do not eliminate the opportunity for students to present their findings orally. They can do this, but the teacher will have to remember to exercise patience and give every student the opportunity to express his or herself. Because if you do not do that, they will go home feeling very dejected that they did all of this work and they were not given the opportunity to express themselves. Now, at the grade 2 level, it's a similar thing. You start off with the characteristics of the grade 2 level in science. What are some things that they're expected to be able to do at this developmental stage? Then you move into the activity. Remember, we said the social studies topic had to do with transportation, and we are using the same flower dough. This time we're targeting the science skills, making observations, communicating, making predictions, and measuring. So the students are now asked to roll out the dough, put it to dry, and they can do some measuring. In that, you could say to them that the pasta should be of a certain length, or measuring could come out when they're actually using the pasta to create their vehicles. And so you could create a challenge. Can you create a pasta vehicle that can transport, let's say, 10 marbles? Now that becomes an engineering challenge. And so this is an opportunity within the inquiry-based method to incorporate the engineering and design process.
Okay, Ms. Baker, there's a hand raised.
Let me just finish and then I'll come back to it.
All right, she'll come back to you, Ms. Davis.
All right, so grade 3, the science characteristics, the characteristics that students are expected to display at this level. Now remember, not all students will display them, and some students may exceed them. So you know your students best, so you are able to be informed by that information when you introduce an activity. Now, remember this topic had to do with social studies again, the aspects of the Jamaican culture. And the students were asked to make a kite in honor of the Jamaican culture. So kite making is fun. Again, the science exists, the science skills that you could target, making observations, communicating, making simple predictions, and measuring. So as I explained earlier, while the students are making the kite, you could choose to give them a challenge of coming up with an adhesive that could be used to put the kite together. Now, the adhesive using the flour and water, you may need a little heat, but if you do not want to do that because of safety issues, you could use another recipe with flour and water. It's on the internet, and allow the students to do that. So you're not going to say to the students, here's flour and water, make an adhesive. You're going to allow the students to discover that they can actually make an adhesive from flour and water that is able to keep the pieces of papers of the kite together. So that's how you do it. And to get to that point, you have to ask some questions. So that's the presentation on inquiry-based instructional approach. the whole idea is that as you give the students activities, you have to remember two things. One, that activity must be appropriate for the developmental level. It must be appropriate for grade 1, grade 2, or grade 3. The second thing, you have to use an instructional methodology that lends itself to developing many of the science skills and practices that we are talking about. You cannot develop these skills through lecturing. And third, you must be prepared to act as a facilitator by asking students questions that will help them to come up with the answers. Now, as a teacher, when you plan your lessons or you plan your units, you have to think about some of these questions beforehand. You can't wait until you're in the classroom situation because you will be bombarded with a number of things. And you have to think on your feet. So you need some of these questions before. I agree that some questions will be spontaneous, but you have to be prepared. But once you use the inquiry-based method, the project-based learning, and any other one of the methodologies that we have mentioned, the students will excel. And they will not only excel in science, they will excel in all subject areas. Thank you very much, my colleagues. And may I hear the question from...
Yes. Okay, thank you. Yes, go ahead, Ms. Davis.
Good afternoon, Miss. It's not really a question of such. I wanted you to just go back to grade 2, the slide before the last one. I would just like to see that slide again, please.
The one with the characteristics of the grade 2 learner?
I think so, just before the last one in grade 2, I think so.
Grade 2.
Not that one?
No, the one
Not that one, the one before.
This one?
Yes.
No.
It's not that one?
Yes, this one.
Yes, it's that one, it's that one.
This one.
Go back.
Oh, okay. This one?
Yes.
Yes.
The characteristics.
The structured inquiry.
Yes.
This one. Yes.
Okay.
Oh, you just want the slide?
Yes.
Okay.
And that one, last one. What's the next one?
All right.
Let me just.
Okay. Remember, don't stress yourself about getting the information on this slide. You will be given the presentation as well as some handouts that list the characteristics of the grade 1 to 3 child in science, language, arts, social studies, and mathematics. So that will be made available to you, so you can use it to, refresh your memories.
Okay, thank you very much, Miss.
All right, colleagues. Yes. So, colleagues, can we thank Ms. Baker? Express your appreciation in the chat. If you have any comments or questions, indicate with your hands raised. She would have given you an idea of some of the skills that we can target at the different grades, what they can actually do, and how we can use the methodologies and the skills we're talking about to get them to develop into these individuals that will love science and are critical thinkers and so on. So as she mentioned, these will be shared. All that we would have shown you will be shared in the Google Classroom. So it's important for you to complete the evaluation form. All right, so we thank Ms. Baker. Yes, thank you. Yes, all the presentations were awesome, right? And we know we crammed it in today, but we were just trying to give you as much as we could. So we thank all the presenters, Dr. Singh Wilmot, Dr. Rowe, Ms. Baker. Thank you, participants. You participated, you asked questions, you gave your comments. Yes, I see some clap hands going on there. All right. Thank you, Ms. Spencer. Okay, guys, so remember to complete the evaluation. When you do that, you get access to a lot more, right? Share with your colleagues, let them know that the session was on YouTube and it will be there. For those who missed it, can go on YouTube, type in grade 1 to 3 skills workshop and actually get the whole session. Before we go, I know you're rushing, But just there's one thing, we didn't have the time to go through this, but let me just address this very quickly. And I tell you, in 2 minutes, you can go. I know that when we look at my body in integrated studies, I have heard the classes, I have seen where teachers are teaching about hypothalamus in the brain and the different divisions and whatever in the brain, the heart and the lungs, and talking about all sorts of structures that they're not supposed to touch at this level. So colleagues, we don't have time, but just go back to the objectives. The objectives tells you exactly what to teach. You're looking at the position of these organs, describing the appearance in simple terms, color, shapes, that sort of thing. And the role in simple terms again, heart pumps blood, brain helps to control the activities of the body, and so on. Not anything too deep, right? Because it is at the grades 1 to 3 level. Same thing for stomach and lungs. You're not to be teaching digestion, colleagues. You're just looking at the stomach, looking at the role it plays in helping to digest foods. That's it. You're looking at the appearance, probably the elastic nature, and so on. And you can carry out some investigations and construct your models and so on. But that is what we require. All right, so another time we'll get into that, but tell your other colleagues, stick to the objectives, stick to the level of the objectives. All right, that's all from me. So colleagues, again, we want to thank you for joining us. We've come to the end of our session. I'll repost the evaluation link in the chat. All right, so you can go ahead and complete, right? We thank JTC for having us and for streaming this. Yes, sir, Ro?
There is a question being posted in the chat. There will be one for grades 4 to 6 as well.
Okay, so for grades 4 to 6, before COVID, we were going around the country doing some skills workshops. So the next time we see grades 4 to 6, we're looking at some concept workshops, but we'll inform you as soon as that is planned, but it should be coming up. If not the end of this next year, as early as possible, we will be putting on that. All right, colleagues, thanks again. Thanks, Miss Solomon. All right. Yes, okay, colleagues. All right, all right. Thanks. Yes, you're welcome, colleagues. No, we don't want you to just get excited and then don't put anything into practice, right? So the only way you can show us that you learned something is to go back and get all these great ideas and come up with some of your own and put them into practice, all right? Okay, there's a raised hand from McDonald. Go ahead.
Yes, I am really excited about science now. My concern is the fact that the students are at home. Maybe they can experiment with their family members. But what when they come back face to face and we are still in the COVID era? How will we get them in terms of the grouping to do some of these experiments?
Right. So you can, some things you can demonstrate. You can still have groupings, just that there are small groupings and they still have to, not bundle up and so on. But I'm sure we can still do that. Have smaller groups, have them bring materials and so on, and space it out around the classroom. If you're doing inside, remember you can go outside. We're advocating for more outdoor learning. All right. Okay. So I think it can be done.
Thank you.
Just go wild and creative. All right. Okay. Any more? Any other comments, questions? All right. No problem. All right, colleagues. If there isn't anything else, I'll just repost the evaluation link for the final time, and then we will